part that I would like to cover with you is a look at the expressions. The next part is to look at the expressions. Okay, so what is the form of the amplification factor for another case of beam column where the loading is different, it's a uniformly distributed load. And this is given in section 3.3 here, beam column with distributed load. And if I can show first what is the amplification factor for this case. So for deflection, they are found to be similar, based on the derivation method which is being used here. And for moment maximum, they are slightly different, but the form, I think the characteristics that we can see, they share a major similar feature, which is they are all divided by 1 over P critical, 1 minus P over P critical, 1 minus P over P critical, 1 minus P over P critical. Just the denominator is a bit different. But here the denominator, they are completely the same. So let's look at how these things are being derived, and then we make a conclusion about the amplification factor in general. So in this particular case class, what we are going to do to derive this is we use Rayleigh-Ritz method. Okay, so it's an approximate method. So we use Rayleigh-Ritz method for beam column with distributed lateral load. What is the amplification factor? So Rayleigh-Ritz method is what you have learned in EAS663. Okay, so this is the beam that we are going to look at, uniformly distributed with the load W, and at the same time there is an axial force P acting. This is X here and this is Y. Now we start in Rayleigh-Ritz method. We start with the bending energy. Here it is being explained here. In general, you have bending. A beam column is subjected to compressions and also load causing bending. So you have axial deformations and bending deformations. Okay, but here we make some we make some assumptions here. In beam column, bending and axial compression usually proceed simultaneously. However, the bending deformation can be assumed to be independent of the axial deformations, as long as the deformation in general remains small. So it will not affect, the axial deformation will not affect too much the bending deformations. So when we want to use Rayleigh-Ritz method to beam column, because of this assumption that we can make, provided that the deformation is small, then the procedure of Rayleigh-Ritz method is the same as Rayleigh-Ritz method that we apply to a beam member. Okay. So we start with the bending energy of the beam. We start with the bending energy of the beam. So the bending energy of the beam is given by these expressions here. So these are the things that you are familiar with. Okay. U is equal to EI over 2. Okay, because EI is constant so that we can take it out. So this is d2y dx2 squared. So this is the lateral deflections of the beam. Then we can get the potential energy of the external load. Potential energy of the external load, which is given by these expressions here. So we have the first term is coming from distributed load. This is a potential energy due to distributed load. And the second term is potential energy due to shortening of members. This is due to the shortening of members, meaning that we have P acting here. And the member deflect, and the member deflect. So this P is going to move this amount here. Okay? Call it delta bar. So this term here that multiplied with P, which is this term here, is equal to how much this load P has moved because this bend. Okay, so this is the one that we will be looking at when we try to apply Rayleigh Ridge method to the case of beam column. So this is the process that we go through in order to get the potential energy of external load. So to get the total potential energy, we just this one strain energy plus the potential energy of external load, which is given by this equation here. Then now in Rayleigh Ridge method, if you can recall, you need to make assumptions about the displacement field, about how this beam column deflect. So this is assumption that we make, which might not be the actual deflections, but we choose one which is kinematically admissible, satisfy the boundary conditions. So this is what we assume here as in the form of sine curve with the delta here. So delta here, which is still the unknown here, is the mid-span deflections. And this is what we want to find. This is what we want to determine. It's the mid-span deflections of this beam column. So we substitute this into these equations, doing all the necessary differentiation first. We come to this equation here. So next we need to do the integrations. We need to do the integration. So this is what happened. And because integration involving sine cosine, so you must be familiar with the integration of sine cosine, the standard form, integration of sine square, integration of cos square, integration of sine, or integration of cos from 0 to L. And with these terms here, what do you get? So these are the standard result of integration formula, which we can make use of, and that gives the total potential energy after integration become like this. So now to use Rayleigh Ridge method, we use the principle of minimum total potential energy, which is del pi p is equal to 0. This is what we apply here. Okay. Then we get to these equations. After applying this means that the differentiations of total potential energy with respect to the delta, which is the unknown that we want to determine, must be equal to 0. This comes from this one here. Okay. Then we get, by solving this, make it equal to 0, we get delta equal to this. So remember our y is equal to delta sine pi x over L. Okay. So this delta is determined by using principle of minimum potential energy in this Rayleigh Ridge method. So we get delta. So we substitute delta into this equation, then we get the y, the deflection curve for the beam column. Now remember, we want to investigate the effect of having axial load. We look at the maximum deflections. So delta gives us a maximum deflection at the midspan of this beam column. So now we further do some manipulations. We do some manipulations, okay, until we get to this equation. So this is the process of some manipulations of the equation, rewriting and then multiply, to do some manipulations in order to get to these equations. And why we want to get to this equation is similar to the previous case. We want to get this, which is a delta subscript 0. This is the deflections when P is equal to 0. When P is equal to 0. So these are the process of getting, so how it is being done. So it's explained here. Okay. We want to get these terms appear. And from these equations, we write to these equations, and also we want to make this P over P critical appear. So these are the process that has been used. Let's go through this and how it is done. So from 3.24, if we introduce these terms here, delta 0 equal to this, then we come to this equation 3.26, which is similar to the case of a beam column with point load at the center. So again, what does this tell us? I think what does this equation tells us? So it again tells us that maximum deflection of a simply supported beam is bent simultaneously by distributed load W and axial force. And of course, in Rayleigh-Ritz method, we make some assumption, we guess of the displacement field. Okay? So it will not be exact. It will not be exact. The y that we get is not exact. So the y that we assume is not exact. So the solution for delta is not exact. But as you can see from the comments made here, and for this case of a beam column with uniformly distributed loads, this reference here, Timoshenko and Gill, have solved this problem analytically, and it is by comparing with the solution here, we can see that the approximate solutions that we make assumption here, y is equal to delta is equal to sine pi x over L, does not differs very much from the exact answer, which is obtained by Timoshenko and Gill in this reference. In this reference, it is not given here, but it has been proven that the solution that we obtained by this assumption in Rayleigh-Ritz method, it only differs not very much from the exact answer. Okay? So we can accept the answer here as a good approximations of the behavior of the beam column. So after we get the equations for delta, then we can get the amplification vector for moment by going through the same process again as in the previous case of beam column. So maximum bending moment is at the midspan for this uniformly distributed. It's at the midspan here. So the maximum bending moment, there are two parts. One is due to this W, and the other one because of P. So again, you can see because of P here, then we get additional moment, secondary moment. So substitute the delta that we have obtained into this equation and do some simplification again. And finally, we come to this form here. Okay. And again, this one is M subscript 0, which is when P equal to 0. So when P is not equal to 0, this will be amplified. So finally, we get to equation 3.30, which is similar to what we have obtained for the previous case. So M max in this case of beam column is equal to M subscript 0, which is this, multiplied with an amplification factor. So again, the amplification factor is very similar in form to the amplification factor for moment maximum for the case of a beam with concentrated load at the middle. That is, if we compare this and this, as I mentioned earlier, they are very similar form. So the maximum deflection for the beam column, if we go through this, I think I would like you to go through this after this and then get to know better what is the full description here. The maximum deflection of the beam column given by 3.26. 3.26 is deflection. Yeah? Deflection is here. This and 3.30, 3.26 and 3.30 are thus both equal to the product of two terms, the maximum deflection or moment, and deflection or moment in the case of P is equal to 0 multiplied with an amplification factor, which consider the effect of the axial load. The most significant in this relation is their similarity, okay, to the corresponding expression for deflection and moment obtained previously for concentrated lateral load. So because they are very similar, so the design of the beam column, we can make use of this similarity in amplification factor to come up with the procedures that we can consider the effect of axial load P. Okay. So it is because of this, it is at least partially because of the similarity of the expressions that we have seen so far for two cases. A relatively simple design criteria can be formulated for beam columns. Now, let me come back to this again. Okay, these two equations, these two set of equations. So they are, this is derived, this has been derived by using differential equation. This has been derived by using Rayleigh-Ritz method. And to obtain this, we do some approximations. Okay, we come to this, and then after we get this, we get this. Here we use Rayleigh-Ritz method, which is already an approximations, but as mentioned in the chapter, the particular location there, this is the solution that we obtain by using Rayleigh-Ritz method for this case, for the deflected curve. It only the difference with the exact solution obtained by other researchers are not very much. So it is a good approximation. The Rayleigh-Ritz method that we have gone through just now. After we get this, then we can get to this here. Okay. Now, in the next slide here, I show you from this particular reference for different loading cases. For these loading cases where you have end moment here, end moment, which is causing the bending, this end moment can come from the can come from these loading applied on the previous span here, on the adjacent span here, or it can be a kind of applied moment here. So then you have uniformly distributed, then you have linearly distributed, then you have point loads here. So we have seen this case and this case, okay, but and in these references, it includes also this case of loading and this case of loading. So this is a primary loading causing bending, and on top of that, we have axial load here. Then the maximum bending moment when P is equal to 0 is given in this column. So this is MO QL square over 8. We have seen this. And this is QL over 4. We have seen this also in our first part of the lectures today. Now I want you to look at this third column here, which is a moment amplification factor. For this particular case, then it depends on what is the kappa value here, which is what is the ratio of this end column to this end column. So they give two different expressions for the amplification factor. This is amplification factor being used. Now for this case, amplification factor for moment is given by this, which is 1 minus cos KL over 2, KL squared cos KL over 2. And for this case, it's more complicated, given by this. And for this case, we have gone through this case, okay? And the moment amplification factor here is given by here 2 tangent KL over 2 KL. So these are being derived and shown in this book here. Now, if we plot all this, okay, if we plot all this one, and this one, okay, with different value of P over PE, with different value of P over PE, and we plot the magnification factor for these four cases: uniform moment, distributed load, triangular load, concentrated load, with different value of P over PE. Then on top of that, we plot another curve, which is just simply 1 over 1 minus P over PE. This dotted line here, this dotted line or dashed line here, which is here, dashed line, okay, a long dashed line. Okay. Then we can see that they are very closely related to each other, very close to each other. And actually, if we have, if you plot this equation or this equation, depending on this kappa value, we plot these equations for different P over PE, we plot this, we get different curve, of course. Yeah, the solid line is for uniform load. This dot for distributed load, somewhere here already hidden or superimposed by other line. And this another dashed line, triangular load. Okay. And concentrated load is somewhere here. Then on top of that, just simple 1 over 1 minus PE is this one, which is this somewhere here. So the first thing that we can see is for this solid line, this line, this line, this line, these four cases, they are very close to each other. And actually, when P over PE is less than 0.2, in this range, they coincide with each other. They coincide very much. We can say that almost they coincide with each other. And as P over PE getting larger, they start to deviate from each other, but still they stay close to each other. And they are very much close to this simplified form, 1 over 1 minus P over PE. So from this diagram, which is adopted from here, then what I want to say here, then the researchers want to say is that, okay, the four amplification factors do not differ from each other a great deal. So they are very close to each other. They are very close to each other. So for practical purposes, the four amplification factors are adequately represented by the much simpler formula. So we can just, instead of using the four very complicated equations, the exact one, we can simplify them and represent all four of them using this single simpler formula, which is 1 over 1 minus P over PE. So this is what this graph is trying to show us. Okay. So for design purposes, and we can use this one as the amplification factor for moment. Amplification factor for moment, which is very much simpler than this one, this one, this one, and this one. Now, class, what I would like to suggest is that you can compare these, compare this amplification factor for this case and amplification factor for this case, okay, which with the amplification factor that we derive, okay? So you compare with this and you compare with this by plotting the graph. By plotting the graph and see, okay, amplification factor versus P over P critical. And you can compare what we derive here, which is some approximation has been introduced. This is using Rayleigh-Ridge method itself is approximations. How far is this deviate from this and this? So if you can plot two set of graph, this one versus this, and then another one is you plot this. This is for point load at the middle. against this. Try to plot and see what you can get. Okay, what you can plot is that you plot a graph with different P over P critical, the amplification factor. The amplification factor, one using this formula, maybe you get something like that, and another one using this one. You get another one and see how close they are to each other. They might be very close to each other. That's why for practical reason, we can represent these things. We can represent these things as approximately, for practical reason, we can represent this as 1 over 1 minus P over P critical. Okay? So try to plot that graphs, I think, with one that we derive and that one that is given here by these researchers in this handbook, in this book here. Now, for beam column, yeah, which is members that are subjected to both bending and axial compressions, when we design them, we need to consider the effect of axial load acting on the column on top of the one load which is causing bending. And this effect that we need to consider because of the additional informations due to the action of the axial load, P, is what we call the P delta effect. Okay. The P delta effect has the two P delta here, both they are P delta. This is P capital delta and P small delta. Both of them are P delta effect, and both of them is secondary effect due to action of P under primary action due to applied load. So these are secondary effects that we need to consider, especially when the P over P critical is the ratio is getting larger. And why we need to consider this is because this causes the member to deform more. Remember the delta with the amplification factor, and because of that, you get more bending moment. The bending moment maximum also amplified. So we need to consider them. So when you listen to the word P delta and P delta, this is the effect of having axial load P acting of a member which is subjected to load causing bending. Bending is the primary action, P is the secondary. Okay. Without bending, you won't get P delta effect. Only when the member is subjected to load causing bending, you will get P delta effect. Now, so this should be considered in design of course, by knowing what are the amplification factors that we need to account for. As summarized here, and we have seen also this is taken care of by using the appropriate amplification factor. Now, P delta effect is P delta, P small delta, and P big delta is shown in this diagram here. And this is taken from this book. Now, P delta effect is at element level. Okay, so you have an element subjected to load causing bending, then you have this deflection delta, and because of the deflection delta, we have, if there is a load P acting here, then you create what we call the P delta effect. This is at the member level. Now this big P capital delta effect, this is at the global level, at the structure level. This happens when one end of this member, because of the load causing bending, is displaced relatively to the other end, like in the cantilever here. Okay, if you have a load acting here, then this will bend. On top of that, if you have axial load acting, then this will cause P delta moment here. Okay, so this is the difference between P delta, small delta, and P big delta. The P small delta effect is considered at the member level, and P delta effect here is considered globally at the structure level. So another way to look at P delta and P delta effect here is by looking at this diagram. So P small delta is more at the element level, where you have these deflections. And then because of that, if the action P is acting, you get additional moment. This P delta effect, this is one example when you have a load causing this frame to sway. Then you have a load causing this frame to sway, which means you have this relative translation here, the delta. Then if you have a P acting here, then this P is going to cause additional moment. So this is what we call the P delta effect and P small delta effect and P big delta effect. We will not go further into the design aspect, I think, but just to I think let you all aware, understand that under the topic of beam column, the effect of having axial load acting on the member, which is primarily subjected to bending load. So that is the understanding that you need to have. And of course, later when we go to design, there are aspects where this beam column, there are aspects of design for beam column that we need to consider the P delta effect. Now, in the last part of today's lectures,